All right, so yeah, we're back. This is exploration 10, 10 8. So let's see. We're still evaluating the consequences of the following statement. That suppose that for all groups G such that order of G equals to p to the n plus 1 times m. Suppose that for all groups such that order of G equals to for all G. How are we going to write this? Well, let's see. Okay. Suppose that for all groups G, right, for all groups G, the order of G equals to p to the n plus 1 times m does not imply that that there exists some subgroup, does not imply that there exists some subgroup h of G such that order of h equals to p to the n plus 1. Well, how else can we write this? Aren't we saying that, well, there exists some G such that order of G equals to p to the n plus 1 times m, and at the very same time, uh, for all h subgroup of G, order of h does not equal to p to the n plus 1. Okay? And we're saying that this is a potential case. This appears to be a correct negation, right? Um, if it were implication, whenever this is true, that is true. But if we're saying it doesn't imply that, it means that there are cases where this statement is true and the other one is not. Right, okay. If that were the case, there'd be no implication. And to say there's, yeah, okay. So let's see if you're convinced by that this is a correct interpretation of saying that order of G equals to p to the n plus 1 times m does not imply that there exists some h such that order of h equals to p to the n plus 1. Okay, so suppose these two statements are true. That actually we found order some group G whose order is p to the n plus 1 times m, and there is no subgroup h, and for all subgroups h of G, order of the subgroup h does never equals to p to the n plus 1. Okay, so what? Lagrange's theorem seems to tell us that the order of h must divide the order of G. Well, aren't we saying then that the order of h must divide p to the n plus 1 times m? Okay, but if order of h does not equal to p to the n plus 1, then what are we saying? Are we saying that the potential values of order of h are either order of h could be of the form p to the theta, right? And in this case, theta has to be less than n plus 1, right? Why? Suppose theta were n plus 1. Wouldn't that mean that we found some subgroup of order p to the n plus 1? But didn't we say that no subgroup can have order p to the n plus 1? Alright, so what are the possible values for order of h? It could be p to the theta. Could it be of the form p to the theta times some m? Could it also be of the form p to the theta times some l, where l is some divisor of m, and l does not equal to 1? Okay. Now, before we even spend our time uh, trying to calculate which case is going to be, we need to think about what we want to conclude. We want to conclude from here that, in fact, there is also that if these statements can be true, it's also the case that if you had some group of order p to the n times m, you're guaranteed to have no subgroup of order p to the n, right? So how does having subgroups of order p to the theta times m, p to the theta times l tell us anything about having a group of order p to the n, right? So maybe if theta equals to n, in that case, wouldn't we need to show that, well, actually the only allowed values for, or like, maybe suppose we show this, that actually there actually exists some subgroup such that, such that, well, order of h equals to p to the theta times m. Okay, the music is messing with us, so let's turn off the music. All right, so let's turn it off. All right, great. So far, well, suppose we show that the order of h actually equals to p to the theta times m, and we showed that theta has to be equal to n. Well, then maybe we're talking there, right? So we could use, actually, can we? Yeah, yeah. So we're saying if the n plus 1 case is false, these are the potential values that the order of h can take. It could be p to the theta, it could be p to the theta times m, it could be p to the theta times some l, and we want to use this to somehow conclude that if we have a group of order p to the n times m, we never have a subgroup whose order actually equals to p to the n. So even if we had order of h equals to p to the theta times m, and we proved somehow that theta equals to n, well, let's first see our best case scenario if the proof would work. If it doesn't, then why even engage in the calculation at all? So if order of h equals p to the theta times m and theta equals to n, then haven't we found some subgroup? We found some subgroup h of g such that, well, order of h equals to p to the n times m, and the induction hypothesis tells us we are guaranteed a subgroup. Yeah, no, this is unlikely, because the group G that we're studying, this group G that we're studying does not have to be the same as the group K that we're, right. They're completely different. This approach doesn't feel promising. It just feels very convoluted, in fact. Unless we can salvage it somehow. Yeah. Yeah, it's unsure whether this approach is going to work at all. But before we eliminate it, we need to have a good reason to eliminate it as a potential solution. So the reason seems to be we're saying that at the nth step we have, well, any group G of order p to the n times m, and we're saying that gives us a subgroup of order p to the n, but the n plus 1 step we could have any group. It doesn't have to be G, it could be any group, and it's unclear how two groups that might be potentially different can be thought of just in terms of the orders of the groups. Well, perhaps that's what Sylow's theorem is trying to tell us, but yeah. This strategy just seems overly complex, and it's unclear what it's doing for us. First, we don't know if order of h. We don't know what order of h is going to be, and even if we did know what order of h was going to be, this h, even if the statement were true that for this h, it's indeed true that. Oh yeah, right. So let's try that. So suppose that actually we found some h and said, okay, for this h subgroup of G, it's indeed true that order of h equals to p to the n times L, but no subgroup L of G, for all L subgroup of H, order of L actually equals to, sorry, does not equal to p to the n. That is, this subgroup H of G that we got has, maybe we show that for all of them this is the case. Sorry, this is not, this is supposed to be p, right, p to the n times m. So even if we show that order of L does not equal to p to the n for any L subgroup of H, that's still just for this special H that we picked. What about other subgroups of cardinality p to the n times m that are not necessarily H? So maybe we could say that, well, whatever group we have can be thought of as a subgroup, but why would it have to be a subgroup of a group of order p to the n plus 1 times m? Yeah, so this approach has too many unknowns. It's unclear that it's going to help us at all. So maybe there's something here, but unlikely. So let's put just a big question mark on the approach. And this really begs the question whether induction will help us at all, or whether it's time to come up with something new. The induction we did was we did induction on the powers of, we got p to the m, fixed them so that the GCD of p and m equals to 1 right here, and then we started inducting on the powers of p. When the power of p equals to 1, when n equals to 1, well, we saw that the base case works, but we assumed that it's true for n, but it was not clear how to move inductively. And in fact, the key problem we have with induction is, what are we inducting on? Sure, we're inducting on n, but this statement here that if order of G equals p to the n times m applies to any group that exists, not just a specific group. So it's hard to see how, maybe the crux of the question really becomes, if we have some group of order such that order of G equals to p to the n plus 1 times m, how is that related to some other group k, let's say, whose order k equals to p to the n times m, right? How are these two groups related, right? It's not clear what the connection is exactly, at least not obvious, it appears. Right, and we just run out of time. What this means is that, so this induction approach may not help us. So that means we need to try something we haven't tried before, something new. And that's what we'll be tackling in the next video. Thank you very much for watching this video, and have a relentless week. Bye.